Welcome back to ece 542. We really only have one more week of class, 3 lectures, and this is the third of the, or one of the 3 remaining lectures in this semester. Although you're going to have 4 pieces of material. So I'm going to provide you with a lecture 8.3 squeezed between lecture 8.2 and lecture 8.4, and it's going to illustrate MATLAB, how you can use MATLAB to help you solve homework problem set number 8. And that's already posted on D2L, so if you see a lecture 8.3 and you're going, what in the world is that? This is 8.1 that we're doing now, and it will focus on material for unit number 8. Before you maybe finish up unit 7, you'll want to make sure and turn in homework number 7, which is due on Saturday. So make sure that you observe that change in schedule. The project for 542 is due on a week from today, as is the teacher course evaluation, and the percentage right now is overwhelming in terms of participation. That was a joke. There hasn't been a lot of participation yet percentage-wise, but I do take the TCE seriously. It is helpful. I don't see that until way after your grades are submitted. It's anonymous anyway, but if I could somehow tell who was saying what with a comment, and a lot of times the comments are coming in maybe shuffled since it's online, and I couldn't necessarily identify your scores with respect to the comments. So I welcome your feedback. Imagine that in a controls class, but I do want to try to improve the class in the future, and that's how I use the TCEs, and it is welcome, your feedback. And I've offered extra credit or points sometimes for participation, but I've never achieved the threshold for the class-wise contribution to get into that extra credit mode. So I don't know if that helps or not. But if you start pushing a high level of participation, then maybe I'll consider extra credit for the TCEs. And I think I can actually tell who has participated, so I wouldn't necessarily have to give the entire class the extra credit. I didn't know that in the past, but I think I can tell who has submitted a TCE after the fact. Just saying. So if you want to give me feedback before the TCEs, in terms of the TCEs, that's welcome also. But moving on, the final is on the 10th. Is that 2 weeks from tomorrow? And it's the last day, and please take note of the time. Make sure that's not conflicting with something else that you might have happening. I need to be aware of that. And homework 8 is going to be, you're going to be held responsible for homework 8 material on the final exam. You won't need to submit it for homework grade if you don't want the extra credit. But if you want extra credit, you can submit homework number 8. Since it's due kind of late in the semester, that's the reason for the extra credit label and the way it's being used to determine your grade. So it won't hurt your grade not to turn it in. It might hurt your grade not to know the material if you can't answer the questions on the final exam. Is that clear? So I give you time to figure out what's going on in homework 8, but it's extra credit, homework 8 assignment. And now I've tried to list office hours for the next couple of weeks, and I guess I spoke too soon when I said Friday's office hour adjustment would be the only time Fridays would get adjusted. Well, I had to adjust it again the next Friday. The rest of the semester, 2 more Fridays, I have to have it from 10 to 11, if that means anything to you. But that will be the first day of finals, I believe, on Friday the 4th of May. And the others I've inserted a Tuesday, so these red arrows indicate modifications to the nominal or standard office hour time slots. That's what those red arrows indicate. Today we're going to be doing unit number 8, and so I know you'll probably be texting all of this information between now and the final and maybe even beyond, so I want to give us a shorthand if you're texting between your peers. CTSS is easier to text than continuous time state space, and DTSS, discrete time state space, is maybe easier than typing out all of that wording or those letters. But if you see C, that's continuous time, D is discrete time, and we're dealing in Unit 8 with state space design, which means that we need to start going back and remembering how to model systems in the state space setting. And that's what we'll do today. And we want to figure out how do we translate between continuous time state space and discrete time state space. We've looked at that before in Unit 4, and what I will do today is sort of start with a summary square where we see how we can go from the time domain, from continuous time into discrete time in both the time domain and in the frequency domain. I'll give you sort of those equations in a summary square, and then we'll work through how to actually go. We've been playing most of the second half of the semester with transfer functions in the frequency domain. Let's now figure out, if somebody gives me a transfer function and I want to do state space design, how can I create a state space representation from that transfer function? We'll look at a different way of doing that today than maybe what we've done in the past. That's one of the tasks for today. And then once we have that model or that representation, then we will look at state feedback. And this looks similar to what we've been doing. We have a K, but now we need to keep track or keep in mind that that K can be a matrix. Now before, it's always been a matrix. It's just been a 1-by-1 matrix. It's been a scalar, but you could view it as a matrix. Now the dimension on K is going to depend on the size or the number of inputs that we have, which is the dimension of the input vector U, and how many state variables we have in our state vector. Remember, now we might have position, velocity, temperature, voltage, current. All of those might be state variables in this X vector. And so if X is 5 components tall, if it's a 5-by-1, then we know that K has to have 5 columns in it. And if we had 2 inputs, then we would have 2 rows in K that would be compatible with U, or K would now be a 2-by-5 matrix. It wouldn't be a 1-by-1. We're now assuming with state feedback that we have access to each one of those state variables, not just the output Y, which the Y could be a linear combination of states. Now we're assuming we have position, velocity, temperature, voltage, current, all independently available. We can then scale those with gain values in this K matrix. Essentially, this KX product is summing those pieces together and forming the input U. And that's now driving our system. Obviously, now we have a lot more independent manipulation of variables, and we should be able to do a lot more, but we have to kind of be cautious when we're doing that. That's the state space or state feedback approach. Then we'll look at what that means in a block diagram, and really it looks very similar to the block diagrams we've been looking at, and we'll go through a process of how we actually build or create this matrix K. Then probably the next time that we get together, or not, depending on design day, but I will be recording hopefully, and hopefully it will work. we'll talk about these issues with full state feedback. One is we assume that the full state vector is available. We also assume the system is controllable, so we'll define what that means. We might talk about a regulator design, and that means then that we don't have a reference input explicitly going into the system. We're just feeding back the signals into the input of the system. We're not telling it to go to an angle if it's an antenna or if it's an airplane or if it's a vehicle. We're not saying go to 10 degrees and it's marching off at 10 degrees. Now we're just saying I want you to respond to initial conditions or a disturbance in a certain way. And the input is feeding back that linear combination of state variables. Obviously, we want to be able to have a reference input in some situations, and so we'll talk about incorporating a reference input and how that might be helpful to command our system to go in a certain way or manipulate or move in a particular manner. Here we are now back into the state space representation, and that L is a time index, little l. We have the state vector x, one time step into the future, the argument is L plus 1, is equal to a matrix phi. Phi is our open loop system matrix, times the state vector plus gamma, that's our input matrix, times the input vector u. And the output here, if we do have a direct feed-through term, it would be plus j u of l. A lot of times we're not going to have that direct connection between the input and the output, but it could exist. If it does, then those paths will be accommodated in this matrix J. And with a state space representation, we have a lot of different dimensions to play with. We have the dimension of our state vector, which we're saying is Nevada, tall, little n. We might have Michigan number of inputs, m, and we might have a state that starts with Q, maybe not. So now we have a Q dimensioned output y. But hopefully you can distinguish between Q, M, and N when I'm talking. In person you can read my lips, but maybe if you're listening to this somewhere at your kitchen table, you maybe can't see my lips, which is a good thing, probably. Anyway. All right, so there's the model in the state space representation, discrete time state space, that's the DTSS, and the block diagram then, here I'm simply highlighting the fact that this delay block is a bank of delays. If our state vector x is Nevada tall, then I have Nevada delay blocks essentially in that block. I don't have just one delay block. I have n different delay blocks sprinkled around in my system, and that will become clear when we start looking at a second order system, that we do have two delay blocks in that second order system. This is the very general form, and you can see in this case I have not introduced the direct feed-through component J in this block diagram, which would connect through a J there, and then I would need to sum the H and the JU to end up with Y is equal to H x of L plus J U of L. And that may not be very visible, but that's okay because it doesn't need to be very visible. In most of the examples, we won't have that direct connection between the input U and the output Y. But I hope you can see why I'm calling that the direct feed forward matrix in this model representation. It directly influences Y. There's no dynamics between the input U and the output Y in that connection. There's no delay. You hit the system with the U, you immediately see that piece in the output Y. Now, here's the challenge, is to copy this in 1 minute. So I'm assuming that you have, now that you're graduating or you're in graduate school, you can immediately copy this down and have it memorized. You have photographic memory. Well, this will be available, obviously, but this is that summary square, and what you really want to be focusing on is the fact that we're going from continuous time to discrete time, and in all of these, we are assuming a zero-order hold equivalent. The top row of boxes is the time domain way of going from continuous time to discrete time, and the bottom row of boxes is actually in the frequency domain. That's, oops, and I forgot to label that, so let me label this. And we could Laplace transform the time domain to obtain the transfer function in the left column, which is in the continuous time setting, or we could Z-transform in the right column the state space representation to derive or obtain the transfer function description in the frequency domain. What we will do today in the very first part is actually go the opposite direction. We want to today start with a transfer function and go up and see if we can find a phi matrix, a gamma matrix. And why did I change notation? Oh, to be consistent with the continuous time. Now my H is actually C, or equivalent to C, and my J is actually D in the output equation, because they carry directly over from the continuous time when I do a zero-order hold equivalent, from the left column to the right column. And below that summary square, I'm showing you how to connect or relate the continuous time matrices A and B to the discrete time system matrices phi and the discrete time input matrix gamma. And we've talked about that before. But this just tries to establish that notation. If you needed to, in the time domain, find, but you can now allow MATLAB to do that for you, so that on the final exam, well, you can't do it on the final, can you? When you get this 10 by 10 A matrix and start trying to find the matrix exponential of a 10 by 10, the final's 2 hours. Did I mention that? So you'll have a few minutes. No, I'm joking on the, I'm going to be called deadbeat again. All of the eigenvalues of phi or phi sub c are going to be at the origin after we control it. But that could be one of our design specifications. Let's now look at this process of finding a discrete time state space from a transfer function. And here's the transfer function that we want. G of z is 3 over z times z minus 2, and I'm hoping at this point in the semester you already are seeing the root locus associated with that transfer function. If you're not seeing the root locus immediately, at least you can start seeing where the poles and zeros are going to be located, I hope, because I've already factored the numerator and denominator into pole zero form. Do I have any open circles on this z-plane? No, I don't have any finite zeros in G of Z. What's the order of the system? Second order. So now when I go into the time domain, I better be expecting 2 delay blocks generically. And I can, I hope, see that I have a pole at the origin and a pole at 2 in this z-plane plot. Now, if I wanted to look at the root locus of this, I'm hopeful that everyone here could quickly sketch the root locus of that pole 0 pattern. Based on what? What's one of the first main features of this system that you might want to keep in the back of your mind in thinking about the root locus diagram? That was kind of a vague question. But what's a critical feature of this system that you might think about relative to the root locus? Pole 0 excess. The pole 0 excess is 2, and what does that tell us? So now we have 2 asymptotes that are going off to infinity. And when we have 2 poles by themselves, those asymptotes are actually where the root locus lies. Our root locus lives right on those asymptotes, and the asymptotes are located, their centroid is averaged between those 2 poles. Or we now have this segment of the real line as a part of the root locus. The pole at the origin is going right, the pole at 2 is going to the left, and they meet halfway between each other, and one goes up and one goes down. And now you might ask yourself, can I stabilize this system with constant output feedback? Can I stabilize this system with constant output feedback? What are you now looking at or thinking about when I say, can you stabilize this system? You're tweaking the gain. You're taking the gain from 0 up to a big value. Infinite is how this is sketched. And what are you looking for as you're adjusting that gain k from 0 up to infinity? You want 2 branches. Since you have 2 branches, you have 2 closed loop poles, you want those 2 closed loop poles to be simultaneously inside the unit circle. The unit circle is there, and as I crank up the gain k, even if I could stay slightly inside the unit circle with that pole that's going from the origin to the right, that pole that's coming in from 2 is never going to go into the unit circle. I'm just going to hit the boundary and then they're going to exit. So I cannot stabilize this system with constant output feedback. So that's maybe one motivation for looking at state space control. Let's look at a different way to introduce flexibility in our control design process, and to do that, we first need to find the system matrices, the phi matrix, the gamma matrix, and the H matrix for this G of Z transfer function. And to do that, the first thing I'm going to do is find a difference equation that connects the input to the output. Or I'm now looking at Y of Z over, let's say, U of Z is equal to 3 divided by Z times Z minus 2. Or that's now 3 over Z squared minus 2Z. I can cross multiply and get one equation. I can now have z squared minus 2z operating on the z transform of the output, and that's equal to 3 times the z transform of the input. And this, as a review for the final, you should be able to immediately take into the time domain, because z represents what in the time domain relative to multiplication by z in the frequency domain. If you just have one z scaling a transformed variable, what's the time domain result? Now we just advance by 1. So the z squared is advancing by 2. This now immediately gives us a time domain system representation in the form of a difference equation. So U is the output of our controller. U is the input to this system. U is not a step input. U is a generic signal. And I'm hoping now at this point in the semester you've become comfortable with that context way of handling or dealing with U of n. U of n in this case is just a generic input waveform. And that will actually represent the output of our controller, or what we want to inject the signal into our plant with. Now what we want to do is actually build an all delay block diagram from this difference equation, and by doing that we'll immediately be able to find a state space representation by labeling the outputs of the delay blocks as our state variable components. And as I'd promised before, we're going to do this maybe a little differently than what we have in the past. And what I'm going to do is I'm going to rewrite that difference equation to where all of the waveforms or signals algebraically sum to 0. Or I'm really just going to subtract 3u of n from both sides of that equation. I'm going to work with, to begin with, u of n plus 2 minus 2y of n plus 1 minus 3u of n equaling 0. That's the same equation. That's the governing difference equation for this dynamical system. This is how the input and the output are related in this system. Now you might skip down a little bit, because now I'm going to start drawing a block diagram, but I want to leave myself some room between this equation and my block diagram. But what I'm going to do is I'm going to, in my block diagram, I'm going to start with an initial summing junction, and injecting into this summing junction, I'm going to put in 0. What? But that 0 now is a special 0. That 0 is the left-hand side, or I could think of that 0 as the left-hand side of that blue equation on the top of the screen. That 0 is actually y at n plus 2 minus 2y of n plus 1 minus 3u of n. That's how the system evolves. And what I'm going to assume is I have access to the input at time n and the output at time n, and I want to use those signals to try to end up with an interconnected all delay block diagram that eventually will produce that dynamical relationship, that linear difference equation. the first thing I'm going to do is I'm going to look at that equation and I'm going to say, do I have a y of n or a u of n that I can add or subtract from that equation to produce a different signal coming out of the output of that summing junction. I said I have access to u of n and y of n. Now I want to look at that equation and say, do I have any of those waveforms? And if I do, I'm going to do what I need to do to eliminate that particular piece of that equation. Meaning, I have a u of n that's scaled by 3 and it's subtracted. What I want to do now is add 3u of n to that so that I start to simplify or reduce what's happening in that equation of relationships. Or now I have y of n plus 2 minus 2y of n plus 1. But what I've done in black, saying plus 3u of n, I need to do in my block diagram. I now need to say, oh, here's u of n. I now want to take that signal, scale it by 3, and inject it into that summing junction. I'm assuming I have access to y of n and u of n. And now I'm taking that u of n, scaling it by 3. That's what I did in the second row up above. And when I add plus 3u of n to that 3-termed left-hand side, I end up with 2 terms. And those 2 terms, if I wanted to, I could call those maybe an alpha 1, and that alpha 1 is right there. That's coming out of that summing junction. I inject 0. So now we have a little bit more classroom participation, and that wasn't on the hammer on the wall, was it? So we've now controlled that process. We now have a notebook that's been distributed back into the right hands. All right, so where were we? Alpha 1. Is it clear where alpha 1 or how alpha 1 is being produced? Now, what can we do? Well, now that we have alpha 1, we said we're going to start working with delays. If we now delay what alpha 1 is, suppose we put this through a delay. What's alpha 2 going to be? So now I'm saying alpha 2 is a delayed version of alpha 1. And maybe I should have given me more space, but now alpha 2 is a delayed version of y of n plus 2 minus 2y of n plus 1. What's that equal to? Are we okay with that analysis or those steps? And I can now use that information to realize that, oh, I said I had access to u of n and y of n, and I want to use those to try to simplify this down to eventually just possessing y of n at the output. If we follow that logic, if y of n is over here, then if I combine alpha sub 2 with what? Will I simplify this alpha sub 2? How do I start pulling off terms or eliminating terms in the alpha 2 expression if I have access to y of n? I can add 2 y of n to that. So that now the sum of those becomes y of n plus 1. And here I now have 2 y of n which gives me alpha sub 3 here. And what's alpha sub 3? It's alpha sub 2 plus 2y of n, which is just y of n plus 1. And do you see how I'm now going to connect up my y of n that I assumed I had access to alpha 3 to produce y of n? Now I just need to pass alpha 3 through a delay. And I have y of n. There is now my block diagram, all delay block diagram, that actually dynamically is the same as this boxed difference equation. That block diagram now has the same dynamical behavior as this linear difference equation. And the reason we wanted to do that is so that now we have this all delay block diagram, I can start labeling the outputs of my delay blocks as state variables, and that will allow me to get my states, my system matrix phi, my input matrix gamma, and my output matrix h. Or let's now just say we're going to label as state variables. And now do you see that I could have a few different ways of labeling those? I'm going to go ahead and label the output of the leftmost summing junction as x sub 2, and the rightmost output of that rightmost delay block I'm going to label as x sub 1. And once I've done that, now hopefully you know what's to the left of that leftmost delay block. What is now alpha sub 1? What's another way of labeling alpha sub 1? This is simply x sub 2 of n plus 1. And what's alpha sub 3? And now I'm good to go. Now I can actually create my state space representation. I just have to use that information. I now know or have signals x sub 1 of n plus 1 and x sub 2 of n plus 1, and I need to write those as a linear combination of the state variables at time n plus the input at time n, where this result is my system matrix phi. What are the dimensions on that? How many rows do I have in phi? That has to be compatible with the x1 of n plus 1 and the x2 of n plus 1, and there are 2 rows of that. And the number of columns in phi has to be compatible with how many rows I have in the state vector, which is 2. This phi matrix always needs to be square. In this case, it's 2 by 2. I have 2 state variables. What are the dimensions on my input matrix gamma for this example? I have 2 rows, and I only had the 1 input, so this is a 2 by 1 matrix. And I should be able to now populate those elements in the system matrix phi and the input matrix gamma. And I can do that by looking back at the block diagram. If I look at x sub 1 of n plus 1, I want to rewrite that in terms of linear combinations of the state vector components at time n and the input at time n. What is x sub 1 of n plus 1? Do I have anything multiplying the input u going into that summing junction? So now I'm looking really at the output of that summing junction is x sub 1 of n plus 1, and I say, what's making up that output? That's just an algebraic relationship. So I look at all of the arrows going into that summing junction, and hopefully they are functions of state variables at the current time and inputs at the current time. One of those signals coming up from the bottom is 2 times the output, but the output in this case is x sub 1 of n. So now I have 2 x1 of n's, and I can see that that's going to be that 1, 1 entry in my phi matrix. That will pull off x sub 1 of n in that product. Then if I move around that summing junction in a clockwise direction, I come up to the next arrow coming into that summing junction, and that one is just x sub 2 of n. That's pretty straightforward to put into this system matrix. That's just needing to scale x sub 1 of n with a scalar of 1. Have I already accounted for all of the signals going into that summing junction? I had 2 inputs going in, or 2 arrows coming into that summing junction and 1 going out. So I've now accounted for everything, and there was no direct input to manipulate x sub 1 of n plus 1. What about x sub 2 of n plus 1? Now I have 0 coming in, so I don't need to worry about that. That I can actually just erase, and I have 3u of n. So I have no states contributing, and I have 3 times u of n. That's my dynamical relationship for this state space representation. What's the output equation? Once I have the state vector defined as a 2 by 1 and the input vector defined as a 1 by 1, and knowing that I only have one output, I can actually put in all of the state matrices dimensionally. This matrix is the output matrix that we were calling H. What are its dimensions? So it's 1 row tall and 2 columns wide. It's a 1 by 2. What's the direct feed-through matrix dimensionally? It has 1 row and 1 column. It's a scalar, but it's a matrix. It's a 1 by 1 matrix. What we now want to do is go up to our block diagram and see what sum, algebraic sum of state variables make up y of n. And this one, it's not very complex. It's just x sub 1 of n. Or we can now fill that in, and we have a 1, 0, 0. Now we have our state space representation for that original transfer function based system. And we can kind of have a little bit of a check on our work by saying, okay, how big was that g of z order-wise? What was the order of g of z? It was second, so we would expect a 2 by 2 phi matrix. How many inputs did we have? 1. So we have one input column, or our input matrix is 1 column wide. How many outputs did we have? 1. So the output is also 1 row high, the matrices in that. Let's now look at what we can do with that using full state feedback. U of L now is equal to minus K X of L. And we could use that relationship to try to inform the dimension on K. Meaning, what's the dimension on the input, U? In general, it's M rows tall and 1 column wide. It's a vector. It's M by 1. And the state vector, X, is Nevada by 1. It's n rows tall and 1 column wide. If that's the case, then generically, K has to be consistent or compatible with those matrices or with those dimensions. Meaning, whatever K needs to be such that when it's multiplied by X, it produces an M by 1 vector. So K has to have how many rows? Has to have M rows, and it has to have N columns so that it's compatible with that matrix product. In our particular example, how big is K? How many rows? What was M? Michigan. Km was the number of components of our input. We had one input. And it has columns consistent with the state vector components, which is n, and in this case, that was 2. 1 was the number of inputs, which generically is m, and 2 is the number of, let's say, state components, which is n. Or now we have 2 variables in our state feedback matrix, capital K. And we want to now use those variables, K sub 1 and K sub 2, to actually change the dynamic behavior of our system. The open loop system in this case had, where were its poles? Where were the poles of this system? 0 and 2. So our open loop system better have poles at 0 and 2, and if you've had some linear algebra, you can see that the eigenvalues of that phi matrix, the system matrix, has eigenvalues. Since it's an upper triangular matrix, it has eigenvalues on the diagonal. It has one at 2 and one at 0. Good, so that should make us feel a little bit better. We want to now use this feedback strategy to actually change that dynamic behavior. It's not acceptable right now. It's unstable. So we want to modify that, want to find this full state feedback gain matrix K to change the system dynamics. And instead of looking that maybe in terms of an equation, let's go back to our block diagram and see if we can sort of visually see this graphically. Our system had two delay blocks. And let me go ahead and just inject my input U here. Whoops. That fed into that delay block to produce x sub 2 of L. And out the second delay block was x sub 1 of L, which in fact was y of L. And we had just a little bit more interconnection in our open loop setting. That's what we had for our open loop system. That was our governing block diagram. And now what we want to do is utilize full state feedback, which means we want to pull off this state, x sub 2, measure it, scale it by a gain value, k sub 2. Let me go ahead and inject the negative sign there so that I don't have to keep worrying about the negative sign at that summing junction. And then I take x sub 1, measure it, scale it by k sub 1, and again I'll go ahead and put the minus sign, and this is now my closed loop interconnected system with full state feedback. I'm measuring each state variable, scaling it, and feeding that back to form. Whoops! Wake me up. Those were supposed to be feeding back to form the U signal, the input. So this now comes in here, and this comes over there, so that U of L, sorry about that, is minus K1 X1 minus K sub 2 X sub 2, and that forms U of L. Or I could now look at my block diagram and say U of L is now minus K1 X sub 1 of L minus K sub 2 X sub 2 of L. But I can rewrite that as minus K1 K sub 2 X sub 1 of L X sub 2 of L, which is minus K X of L. That's now from the block diagram. Let's look at what that does if we now insert U of L equal to minus K X of L into our equations. So now let's look at this full state feedback in terms of equations. And see if these equations now inform how we can design or put together this K matrix. There's our system dynamics in state space form. With full state feedback, we're letting U of L equal minus K X of L. And what we want to do is now use that right there. Or we're going to replace little U of L in this equation with minus K X of L. We now have X of L plus 1 is equal to phi x of L plus gamma times a minus k x of L. And that minus is not a subtraction. Is that clear? That's a scaling. I hope that's clear. I'm not saying gamma minus kx of L. That doesn't make sense. They're not compatible. I'm multiplying gamma times k, a negative k. Or this now is going to be x of L plus 1 is phi x of L minus gamma k x of L. And the x of L is common to both of those terms on the right-hand side, or x at time L plus 1 is now phi minus gamma k x of L, and this is now a new system matrix. It's actually our closed loop system matrix I'm labeling phi sub c. This is now our closed loop. And the idea is that now helps us because now we have the ability to manipulate this gain matrix K to adjust the eigenvalues of phi sub c. Let's see what this phi minus gamma k looks like when we substitute in these variables k being k sub 1, k sub 2 with our example. We want to now build this up. Phi sub c is phi minus gamma k, or phi sub c is now, what was phi? What was its 2 by 2? It had 4 elements in it. It was 2100 reading row-wise, minus gamma. What did gamma look like element-wise? Nothing in the top row, and 3 in the bottom row. And k, we partitioned or labeled k sub 1 and k sub 2. And now we simply need to do this matrix multiplication on the right. I'll do this in a few steps so that it's clear where things are going from. And now the top row is going to be 0 times k1, k2, meaning that comes through with nothing. And the bottom row is just going to be 3 times that vector, that row vector, k1, k2, or now I have 3 k1 and 3 k sub 2. Or I can now do that algebra element-wise. I have 4 subtractions to perform for the 1, 1, the 1, 2, the 2, 1, and the 2, 2 entry. And I end up with phi sub c, my closed loop system matrix, in terms of yet to be determined k's will be 2 and 1. I'm not changing that top row since I'm subtracting 0 from each of those. And in the second row I have minus 3k1 minus 3k sub 2. And if you were really good with matrices and eigenvalues, you could immediately know what k1 and k2 should be to give you a certain collection of eigenvalues. But we're not expecting that. So let's figure out how we can relate an equation in terms of these k's to another equation that we might desire. And to do that, let's find the eigenvalues of this matrix in terms of these unknown k's. and we are going to label that as our, or as a particular polynomial. We'll just call it delta sub k of z. So this full state feedback polynomial we'll call delta sub k of z is now just the determinant of zi minus phi sub c. That's how I find the eigenvalues of a matrix. It's just the determinant of some variable z or lambda. You maybe have seen it as lambda in a math class. Lambda I minus the matrix. How big is I, the I matrix, in this determinant? It has to be compatible with phi sub c. It's 2 by 2. And I'm going to now use vertical bars to represent the determinant. And now I have z times this 2 by 2 matrix minus phi sub c, which I just calculated is 2, 1 in the top row, minus 3k1 and minus 3k sub 2 in the bottom row. Trying to do this in multiple steps so it's clear where all of this might come from. And now I can do the multiplication by z along the diagonal and add those, and I now am looking to find the determinant of a 2 by 2 matrix, where that 2 by 2 matrix in the 1, 1 entry is z minus 2. What's the 1, 2 entry? Top row, second column. It's 0 minus 1. The 2, 1 entry is 0 minus a minus 3k, k sub 1. And the 2, 2 entry now has another z. It's z plus 3k sub 2. And I now want to find the determinant of that 2 by 2 matrix. And that shouldn't be hard. It's the product of the diagonals minus the product of the off diagonals. Or that's now z minus 2 times z plus 3k sub 2 minus 1 times 3 k sub 1. Product of the diagonals minus the product of the off diagonals. And now if you're used to using foil, foil for first, outer, inner, last for the product, for this product of two linear factors in z, I now have z squared plus a minus 2 plus a 3k sub 2 times z minus 6k sub 2. And then I can't forget that last term that's hanging out there. I just need to change the sign of minus 3k1. And I now have plus 3k sub 1. And that is actually my polynomial of the closed loop eigenvalues, or that's the characteristic polynomial in terms of my unknown k1 and k2, and I want to pick k1 and k2 to give the roots of this desired locations in the complex z-plane. And I might refer to that as equation star later on, but that's delta sub k of z. That's now this polynomial, and do you see that in this particular situation I have unlimited ability to manipulate those two coefficients, the linear term and the constant term, because I have k1 and k2 appearing in both of those. So I should be able to locate the poles of this anywhere I want, and what would be an easy location for the closed loop poles? Deadbeat. So now if it's at the origin, what would you want delta sub k of z to be? You would want it to just be z squared, right? That would have two values of z right at z equal to 0. That then tells you that you would want minus 6k sub 2 plus 3k1 equal to 0, and you would also want minus 2 plus 3k sub 2 equal to 0. And you could solve that sort of sequentially, first for k sub 2 and then for k sub 1, and you're done. I see some heads going in the wrong direction. So now, if we wanted this to be a deadbeat response, if we wanted to do full state feedback with a deadbeat response, we would want this polynomial to look, how would we want this polynomial to look? If we wanted the roots of that to be at the origin, we wanted two roots at the origin, delta sub k of z would have to be z squared. Is that clear? If we want that to be z squared, then we need to lose the right two terms, and that's how I found an equation to solve for the first coefficient and the second coefficient. Let's do it a little bit more generically. Let's say, let's design, so now I just quickly did that in case we ran out of time, and we don't want to run out of time. So let's look at how we might say we are designing K in general. Or what's the process for finding the elements in this full state feedback gain matrix K? In our example, K had two unknown parameters, k sub 1 and k sub 2. The first step in trying to find those is, one, to focus on or decide where we actually want our closed loop poles. So we now need to decide on desired closed loop poles. In that last little verbal discussion, what did our desired closed loop pole polynomial look like? It was deadbeat, so we had a second order that was just z squared. Let's do it a little bit differently. Suppose that somebody said, I want my desired poles, I'm calling those z sub delta since we always put these triangles as our desired poles in the previous discussion. I want that to be at 0.8 plus and minus j 0.2. Just for grins. So now, if that's where we want our poles, we now need to produce a desired polynomial that's obviously different than a deadbeat. A deadbeat would just be z squared. Now we want to have some values for the linear coefficient and the constant coefficient. So step 2 is to go ahead and create the desired characteristic polynomial. And we're going to call that delta desired of z. Now we say, oh, I want one root to be at 0.8 plus j 0.2. So z equaling 0.8 plus j 0.2 will cause that to vanish. And I want the other one to be at the conjugate, so now I need it to be at z minus 0.8 plus j 0.2. But FOIL worked so well before when we were baking our potatoes. No, when we were multiplying these linear coefficients. And we can do that again if we just sort of say, oh, here is a first piece, and here is our second piece. And if we use FOIL, do you see that the outer and inner cancel because of the conjugate nature of these roots? So that now, by doing FOIL, we have z minus 0.8 squared minus j squared times 0.02 squared, but j squared is minus 1, and subtracting that, we have a plus 0.2 squared. And we could have actually started with this description, knowing what we now know happens by multiplying these conjugate roots out. So if somebody said, oh, I want poles at 0.8 plus and minus j.2, we can immediately write down the polynomial in this factored form. Or this now says that we want z squared minus 2.8 times z, or minus 1.6z, plus 0.8 squared plus 0.2 squared. And now we know what delta sub d of z needs to be. That's going to be z squared minus 1.6z plus 0.68. And that's going to be my double star. That's my desired polynomial. Before, when we said it was deadbeat, those last two terms were missing because we wanted the roots to be such that z equal to 0 solved that second order. Here, if you substitute in either of those two, 0.8 plus and minus j.2, that will cause that delta sub d of z to vanish. We're almost finished. Now what we need to do is equate, in the third step of this finding k, we want to equate the coefficients in the two polynomials, where that's star and double star, to find k. Or, said another way, that's making delta sub k of z equal delta sub d of z. And in our example, what did we have? Well, in our example, delta sub k of z was z squared minus, or plus, a minus 2 plus 3 k sub 2 times z plus 3k1 minus 6k sub 2. And we want that to equal delta sub d of z, which was in fact equal to z squared minus 1.6z plus 0.68. And now do you see what we can do? We have two equations and two unknowns when we equate coefficients of the linear factor of z and the constant factor of z. If we equate coefficients, or like powers of z, then comparing the z to the 1 coefficient, I have minus 1.6 for the delta sub d polynomial, and that needs to be minus 2 plus 3k sub 2. And that's one equation and the one unknown. I'm just going to write down the answer, and you can verify that tonight. K sub 2 is now 0.133, and the z sub 0 coefficient, or the constant coefficient, is now 0.68 in the delta sub d, and that's equal to 3k1 minus 6k sub 2. I already know what k sub 2 is, and k sub 1 now is going to be almost 0.5. It's just a little bit shy. And that now says that our full state feedback gain matrix K is going to be 0.4933, that's K1, and 0.133 to achieve the closed loop poles at 0.8 plus or minus J.2. And that's how we will conclude this class. Pardon? So there is a controller. U of L is now minus K x of L. So now it's a constant controller, but that controller is scaling each component of the state vector. So now we really have two individual signals that we're combining to create more effective control over our system. And this is now our full state feedback gain that we set out to find.